Welcome to quantum physics. The science that reveals reality is far stranger, far more mysterious, and far more wonderful than our everyday experience could ever prepare us for. It's a realm where particles can be in two places simultaneously, where the act of observation literally creates reality, and where the universe operates according to rules so bizarre that even Albert Einstein, one of its pioneers, spent the rest of his life trying to prove it couldn't be true. He failed, and his failure revealed something profound about the cosmos we inhabit. Tonight we're going to explore the quantum mysteries that govern existence itself. We'll discover why the sun shines, how life emerged on Earth, and what consciousness might actually be made of. We'll journey into a world where common sense goes to die and wonder is reborn, where the impossible happens billions of times per second in every cubic centimeter of space, including inside your own body. So settle in, get comfortable, and prepare to have everything you thought you knew about reality fundamentally transformed. Picture yourself standing in your backyard on a quiet evening. The world around you seems perfectly solid and predictable. Drop a ball, and gravity pulls it down to the ground with reassuring consistency. Push a door and it swings open on its hinges, following paths you can trace with your eyes. Turn on a flashlight and photons travel in straight lines from the bulb to whatever surface they strike, illuminating objects exactly as you'd expect. Everything behaves according to rules that have been understood for centuries. It's a clockwork universe, rational and orderly, governed by cause and effect in ways that seem utterly transparent. The chair you're sitting in right now feels absolutely solid. If someone asked you to describe it, you'd say it's made of wood or metal or plastic, materials that are clearly continuous, unbroken, substantial. The wall behind you seems equally solid, an impenetrable barrier that light can't pass through and your hand can't penetrate. The floor beneath your feet supports your weight without question. These aren't just appearances. They're the direct testimony of your senses, confirmed by every interaction you've ever had with the physical world. How could they be illusions? But here's the extraordinary truth that quantum physics reveals. The truth that changes everything once you understand it. Every single atom in your body, every particle of matter around you, every photon of light illuminating the scene, is secretly obeying quantum mechanical laws that would seem completely impossible if you encountered them directly in your everyday life. Those walls that appear so impenetrably solid, they're actually mostly empty space, more void than substance by a staggering margin. If you could somehow see atoms at their true scale, you'd find that the solid matter occupies only about 1/1,000,000th of the volume. The rest is empty space, held together not by solid substance, but by electromagnetic forces that exist in probability distributions rather than definite locations. The nucleus of an atom, containing nearly all its mass, is incredibly tiny compared to the electron cloud surrounding it. If you scaled up a hydrogen atom so that its nucleus was the size of a basketball sitting at the center of a stadium, the electron would be a tiny speck orbiting somewhere outside the stadium walls. Everything in between, empty space. And yet the atom seems solid to us because the electromagnetic forces are strong enough to prevent other atoms from easily passing through. Those electromagnetic forces themselves are quantum mechanical in nature. They're mediated by virtual photons, fleeting quantum entities that pop into existence for incredibly brief moments, facilitate the interaction between charged particles, then disappear before the universe's uncertainty principle notices they've borrowed energy. The stability of matter itself depends on quantum mechanics. The electrons surrounding atomic nuclei don't orbit like planets around the Sun, as early models suggested. They exist in quantized energy levels, probability clouds where they're simultaneously everywhere and nowhere until observed. If they behaved classically, they would radiate away their energy and spiral into the nucleus in a fraction of a second. Matter as we know it couldn't exist without quantum mechanics. The light from that flashlight? It's simultaneously behaving as both a wave and a particle, existing in multiple quantum states until the moment it interacts with something. The ground beneath your feet? It's a seething foam of virtual particles popping into and out of existence faster than your mind can comprehend, borrowing energy from the future and paying it back before the universe notices. This isn't science fiction or philosophical speculation. This is the established, experimentally verified foundation of physical reality. We know this because quantum mechanics is the most precisely tested scientific theory in human history. Its predictions have been confirmed to extraordinary levels of precision, sometimes to more than 10 decimal places. The computer or phone you're using to watch this video operates because engineers have learned to harness quantum effects in semiconductors. The GPS system that guides you through unfamiliar streets works because it accounts for quantum mechanical effects on time itself. The sun that warms your face and powers all life on Earth shines because of quantum fusion processes occurring in its core. You literally couldn't exist without quantum mechanics. Yet our brains evolved to navigate a classical world of medium-sized objects moving at moderate speeds. We developed intuitions about how things work based on our everyday experience with basketballs and bicycles, doors and dishes. These intuitions serve us well in daily life, but they become spectacularly wrong when we zoom down to the scale of atoms and subatomic particles, or when we consider the fundamental nature of reality itself. It's as if we've spent our entire lives swimming in an ocean, only to discover that the water we thought was simple and transparent is actually teeming with invisible, impossible creatures following rules that defy everything we thought we knew about swimming. The story of how scientists discovered the quantum world is one of the most fascinating chapters in the history of human thought. It begins in the late 1800s, an era when physicists believed they had nearly figured out the fundamental laws of nature. Classical physics, built on the elegant foundations laid by Isaac Newton, James Clerk Maxwell, and others, seemed to explain everything from the motion of planets to the behavior of light and electricity. The universe appeared to be a vast, predictable clockwork mechanism. If you could somehow know the exact position and velocity of every particle at any given moment, you could, in principle, calculate the entire future and past of the cosmos with perfect precision. Everything was deterministic, governed by mathematical laws that left no room for genuine randomness or uncertainty. But then, cracks began to appear in this beautiful, orderly picture. Scientists started noticing phenomena that simply didn't fit the classical framework, no matter how much they tried to force them into it. When physicists heated objects and studied the spectrum of light they emitted, the results stubbornly refused to match theoretical predictions. Classical theory predicted that heated objects should emit infinite amounts of energy at high frequencies, which was obviously absurd, since it would mean every hot object should immediately radiate away all its energy in an ultraviolet catastrophe and instantly cool down. But this didn't happen. Something was fundamentally wrong with the theory. Similarly, when scientists shined light on certain metals and observed electrons being ejected from the surface, a phenomenon called the photoelectric effect, The behavior was utterly baffling according to classical theory. Classical physics predicted that brighter light should eject electrons with more energy, and that any frequency of light should eventually liberate electrons if you made it intense enough. But experiments showed something completely different. The energy of ejected electrons depended only on the color or frequency of the light, not its brightness. Red light, no matter how blindingly intense, couldn't eject electrons from certain metals, while even dim violet light could knock them free immediately. It was as if some fundamental property of light that classical physics couldn't account for was at work. And when physicists tried to understand how atoms could possibly be stable, classical physics offered no satisfactory answers whatsoever. According to classical electromagnetic theory, electrons orbiting an atomic nucleus should constantly emit radiation as they accelerate, lose energy, and spiral inward until they crash into the nucleus in a fraction of a second. Every atom should be catastrophically unstable, and matter as we know it shouldn't exist. Yet atoms are stable. You are stable. Something was deeply, fundamentally wrong with classical physics. These weren't minor inconsistencies that could be swept under the rug or explained away with small corrections. They were fundamental problems that threatened to topple the entire edifice of 19th century physics. And from these cracks emerged a revolution that would transform not just our understanding of the physical world, but our entire conception of what reality actually is. The first quantum pioneer was Max Planck, a rather conservative German physicist who was trying to solve what seemed like a mundane technical problem about the radiation emitted by heated objects. He wasn't trying to revolutionize physics. He was just trying to make the mathematics work. But in the process, he stumbled onto something extraordinary. In 1900, Planck discovered that he could solve the blackbody radiation problem by making a radical assumption. What if energy wasn't continuous like water flowing from a tap, but instead came in discrete, indivisible packets? He called these packets quanta, from the Latin word meaning how much. This was revolutionary in ways that Planck himself didn't fully appreciate at first. For centuries, scientists had assumed that energy was smooth and continuous, that you could always divide it into smaller and smaller portions without limit. But Planck's quantum hypothesis suggested that at the smallest scales, energy comes in specific, unchangeable units, like coins that can't be divided. It was like discovering that what appeared to be a smooth ramp was actually a staircase when viewed up close. The steps are so small that we don't notice them in everyday life, but they're real nonetheless, and they fundamentally change the nature of reality. Planck himself was uncomfortable with this idea. He thought of quantization as a mathematical trick, a convenient assumption that happened to give the right answers without necessarily reflecting something true about nature. It took Albert Einstein to recognize that Planck's quanta represented something far more profound about reality itself, something that would shake physics to its foundations and eventually lead to technologies that would transform human civilization. Einstein's insight came from studying the photoelectric effect I mentioned earlier. Classical physics predicted that the energy of ejected electrons should depend on the intensity of the light, essentially how many electromagnetic waves were hitting the metal surface. But experiments stubbornly showed that the energy depended only on the frequency, the color of the light, not its intensity. Einstein realized that light itself must come in discrete particles, quanta that he called photons. Each photon carries a specific amount of energy determined by its frequency. Bright light simply means more photons, not more energetic photons. This explained the photoelectric effect perfectly. A red light photon, no matter how many companions it has, carries too little energy to knock an electron free from certain metals. But a single violet photon carries enough energy to do the job. It's not about how much light you have. It's about the energy of each individual packet. Einstein won the Nobel Prize in 1921 for this work, not for his more famous theory of relativity. But Einstein's photon concept created a profound puzzle that persists to this very day. You see, by the early 1900s, scientists had already proven beyond any doubt that light behaves as a wave. It diffracts around obstacles. It creates interference patterns when waves overlap, with bright fringes where peaks meet peaks and dark fringes where peaks meet troughs. It exhibits all the characteristics we associate with wave phenomena. There was no question that light was a wave. Except now Einstein was saying light also behaves as discrete particles, photons with definite energies and, in a sense, definite positions. How could light be both a wave and a particle simultaneously? This wave-particle duality became one of the central mysteries of quantum mechanics, a puzzle that we're still grappling with today. Light seemed to have a split personality, sometimes acting like waves spreading through space, other times behaving like discrete particles with specific locations and energies. Even more bizarrely, the behavior you observed seemed to depend on what kind of experiment you performed, as if reality itself was fundamentally ambiguous until forced to choose by the act of observation. But the strangeness was just beginning. As scientists developed more sophisticated ways to study atoms and subatomic particles throughout the 1920s, they discovered that matter itself exhibited this same schizophrenic behavior. Electrons, which had always been thought of as tiny particles orbiting atomic nuclei like miniature planets around a sun, also displayed wave-like properties under certain conditions. In 1927, Clinton Davison and Lester Germer fired electrons at a crystal and observed interference patterns, the telltale signature of waves. Particles were behaving like waves. Waves were behaving like particles. Nothing made sense anymore. This led to one of the most beautiful and bizarre insights in the history of science. A young Danish physicist named Niels Bohr proposed that electrons in atoms could only exist in specific, quantized orbits around the nucleus, just as Planck had quantized energy and Einstein had quantized light. Bohr quantized angular momentum. Electrons could jump between these allowed orbits by absorbing or emitting photons of specific energies. But they couldn't exist in the spaces between orbits. It was as if an elevator could only stop at certain floors, never anywhere in between. Bohr's model worked remarkably well for explaining the light emitted by hydrogen atoms. When electrons jumped from higher energy orbits to lower ones, they emitted photons with precisely the wavelengths observed in laboratory spectra. But this model raised profound questions that cut to the heart of reality itself. If electrons could only exist in specific orbits, what happened when they jumped from one orbit to another? Did they travel through the intervening space? Or did they somehow teleport instantaneously from one location to another? And perhaps most troubling of all, where was an electron between measurements? The answer, when it finally crystallized in the late 1920s through the work of Werner Heisenberg, Erwin Schrödinger, and others, was stranger than anyone had imagined. Electrons don't have definite positions or velocities until they're observed. Instead, they exist in what physicists call superposition states, ghostly probability clouds that encompass all possible locations and energies simultaneously. The electron isn't hiding at some definite position that we just don't happen to know. It genuinely exists in a state of indefinite position, spread out over space like a wave, until something interacts with it and forces it to choose a specific location. This is where quantum mechanics becomes truly mind-bending, where it departs completely from anything in our everyday experience. In the world we navigate daily, objects have definite properties whether we're looking at them or not. A baseball has a specific location and velocity, even when no one is watching it. The moon is up there in the sky at a particular position, regardless of whether anyone happens to be looking at it at that moment. This seems like simple common sense. But in the quantum realm, particles don't work this way at all. An electron genuinely exists in a superposition of all possible states until the moment it's observed or measured. It's not just that we don't know where it is. It doesn't have a definite position until something forces it to choose one. Imagine if you could be simultaneously sitting in your chair, standing in your kitchen, and lying in your bed, all at the same time, only collapsing into one specific location when someone looked at you. This sounds absurd, but this is precisely, experimentally, verifiably how quantum particles behave. And it's not just a limitation of our measurement techniques or a quirk of our experimental apparatus. The superposition is real. The collapse upon observation is a fundamental feature of quantum reality. This has been confirmed in countless experiments over nearly a century. In fact, just in 2025, physicists at MIT performed an extraordinarily precise version of the double-slit experiment, stripping it down to its quantum essentials using individual atoms and single photons. They confirmed with unprecedented precision that the more information you obtain about a particle's path, the more the wave-like interference pattern diminishes. They settled a nearly century-old debate between Einstein and Bohr, demonstrating definitively that Einstein was wrong about this particular aspect of reality. Observation fundamentally changes what's being observed. Let's explore one of the most famous demonstrations of quantum weirdness, an experiment so important that physicist Richard Feynman called it the phenomenon which contains the only mystery of quantum mechanics. It's called the double-slit experiment, and it's both elegantly simple and profoundly disturbing. Here's how it works. Take a barrier with two narrow, parallel slits cut into it. Shine a beam of light at the barrier. Some of the light passes through the slits and hits a detection screen on the other side. What pattern do you see? If light was simply particles, little balls of energy flying through space, you'd expect to see two bright strips on the screen, one behind each slit, like if you sprayed paint through two slots in a fence. But that's not what you see. Instead, you see an interference pattern, a series of alternating bright and dark bands spread across the screen. This is the unmistakable signature of waves interfering with each other. Waves coming through one slit meet waves coming through the other slit. Where the peaks of the waves align, they add up to create bright fringes. Where a peak meets a trough, they cancel out to create dark fringes. This interference pattern proves that light is behaving as a wave, spreading out from both slits simultaneously and interfering with itself. But remember, Einstein showed that light also comes in discrete particles, photons. So here's where it gets truly weird. What if you turn down the intensity of the light so much that you're sending individual photons through the apparatus one at a time? Now there's literally only one photon in the apparatus at any given moment. It has to go through one slit or the other, right? It can't be in two places at once. Except that's exactly what happens. Even when you send photons through one at a time, the interference pattern still builds up on the detection screen, photon by photon. Each individual photon seems to somehow pass through both slits simultaneously, interfere with itself, and land at a position determined by that interference. It's as if the photon travels through both slits as a wave, but arrives at the screen as a particle. The single photon exists in a superposition of going through both slits until it's detected on the screen. But wait, it gets even stranger, even more philosophically disturbing. What if you try to catch the photon in the act of doing something impossible? What if you place detectors at each slit to see which slit each photon actually passes through? Now, surely you can observe the photon going through one slit or the other while still getting the interference pattern on the screen, right? Surely you can have your cake and eat it too, observing both the particle nature and the wave nature simultaneously? Wrong. Completely, utterly, demonstrably wrong. The moment you add detectors to determine which slit the photon passes through, the interference pattern disappears entirely, vanishes, gone. The wave-like behavior evaporates as if it never existed. Instead, you see exactly what you'd expect for classical particles traveling in straight lines. Two bright strips on the screen, one behind each slit, with no interference fringes whatsoever. The mere act of trying to observe which path the photon takes fundamentally changes its behavior, transforming it from a wave that goes through both slits into a particle that goes through just one. It's as if the photon knows it's being watched and decides to behave differently depending on whether anyone's looking. But it's not really about knowledge or consciousness or watching in any ordinary sense. It's about information. The key insight, developed over decades of research, is that whenever information exists in the universe about which path was taken, the interference pattern disappears. It doesn't matter if a human looks at that information. It doesn't matter if anyone ever will look at it. The mere existence of that information, encoded somehow in the physical state of the detectors or the environment, is enough to destroy the wave-like behavior. This gets at something profound and disturbing about the nature of reality itself. In classical physics, we assume that objects have definite properties independent of observation. The moon is up there in the sky at a particular position, regardless of whether anyone happens to be looking at it at that moment. A baseball thrown through the air follows a definite trajectory whether anyone tracks it or not. Reality is what it is, objective and observer independent. We merely discover it through measurement. But quantum mechanics suggests something far stranger and more radical. A quantum particle doesn't have a definite path until information about that path is somehow encoded in the universe, until something interacts with the particle in a way that makes its trajectory determinate. Until then, the particle genuinely takes both paths simultaneously. It's in a quantum superposition of all possible paths. This isn't a statement about our ignorance or the limitations of our measuring equipment. It's a statement about physical reality. The particle really, truly, actually doesn't have a definite path until it's measured, or until information about its path comes into existence through some interaction with its environment. This was demonstrated with stunning precision in 2025 by researchers at MIT, exactly 100 years after the Einstein-Bohr debates about the double-slit experiment. Using ultra-cold atoms trapped in optical lattices as slits and individual photons as the particles being tested, they performed the most idealized version of the double-slit experiment ever conducted. They stripped the experiment down to its absolute quantum essentials, using single atoms and single photons with extraordinary control over quantum states. What they found confirmed quantum mechanics with unprecedented precision. They measured both the interference pattern and the information about which path photons took, demonstrating quantitatively that the more information exists about the particle's path, the more the wave-like interference pattern fades. The relationship is exact and unavoidable. It's encoded in a mathematical inequality that shows a trade-off between path information and interference visibility. You can't have both. The universe simply doesn't allow it. This 2025 experiment essentially settled the nearly century-old debate between Einstein and Bohr. Einstein had argued in 1927 that you should be able to detect the recoil of the slits when a photon passes through, thereby determining which slit it went through, while still observing interference. He thought this would catch quantum mechanics in a contradiction. Bohr responded using the uncertainty principle, showing that the detection of recoil would necessarily introduce enough uncertainty to wash out the interference pattern. The MIT experiment proved Bohr right with atomic-level precision whenever an atom was rustled by a passing photon. Whenever any information about the photon's path was encoded in the quantum state of the atom, the interference pattern was correspondingly diminished. The more rustling, the more path information, the less interference. The relationship was quantitative, measurable, undeniable. Wolfgang Ketteler, one of the researchers and a Nobel laureate in physics, noted that Einstein and Bohr would have never thought it possible to perform such an experiment with individual atoms and photons. But we can now, and the results vindicate quantum mechanics completely. This gets at something profound about the nature of reality itself. In classical physics, we assume that objects have definite properties independent of observation. The moon is up there whether anyone looks at it or not. But quantum mechanics suggests something far stranger. A quantum particle doesn't have a definite path until that information is somehow encoded in the universe, until something interacts with the particle in a way that makes its path determinate. Until then, it genuinely takes both paths simultaneously. Recent experiments have pushed this strangeness even further. In so-called delayed choice experiments, scientists can decide whether to measure which slit a photon went through, even after the photon has already passed through the slits and is on its way to the detection screen. Remarkably, this later choice seems to retroactively determine whether the photon behaved as a wave passing through both slits, or as a particle passing through just one. The future measurement influences the past behavior. Causality itself becomes questionable. What does this all mean? That's the question that has haunted physicists for a century and continues to spark heated debates today. In 2025, during the International Year of Quantum Science and Technology, physicists gathered at a conference on the German island of Helgoland, the very place where Werner Heisenberg first formulated quantum mechanics 100 years earlier. The debates got so intense that physicists were literally yelling at each other aboard a ferry crossing the North Sea, arguing about what quantum mechanics really tells us about reality. One physicist shouted, "What do you mean, what do I mean?" as the boat pitched and rolled. A century after its founding, quantum mechanics remains one of the most successful, yet poorly understood theories in all of science. Now let's explore one of the most counterintuitive and important aspects of quantum mechanics. A phenomenon so strange that it makes virtual particles look tame by comparison. It's called quantum tunneling, and it's the reason you exist. Here's the basic idea. In classical physics, if a particle doesn't have enough energy to get over a barrier, it can't get to the other side. Period. Imagine rolling a ball toward a hill. If the ball doesn't have enough kinetic energy to reach the top of the hill, it will roll partway up, slow to a stop, and roll back down. It can't magically appear on the other side of the hill. The energy requirements are absolute, but in quantum mechanics, things work differently. Remember, particles are described by wave functions. Probability distributions spread out in space. Even when a particle doesn't have enough energy to classically overcome a barrier, there's a small but non-zero probability that its wave function extends to the other side of the barrier. And if the wave function is there, the particle can be there. The particle can tunnel through the barrier, appearing on the other side without ever having enough energy to go over the top. It's as if the particle can walk through walls. This sounds like science fiction, but it's not only real, it's essential to the operation of countless technologies and natural processes. Quantum tunneling isn't some rare exotic phenomenon that only happens in carefully controlled laboratory experiments. It's happening all around you, all the time, in ways that are absolutely critical to your existence. The most important example of quantum tunneling in action is nuclear fusion in the Sun and other stars. This is quite literally the reason you exist, so it's worth understanding in detail. Here's the fundamental problem that quantum mechanics solves. The core of the Sun reaches temperatures of about 15 million degrees Celsius. That sounds incredibly, unimaginably hot, and it is by any human standard. You couldn't survive even a fraction of that temperature. But here's what's shocking. It's actually not nearly hot enough for nuclear fusion to occur according to classical physics. Not even close. Here's why this creates such a profound puzzle. Hydrogen nuclei are just protons, particles with a positive electrical charge. Like charges repel each other. A fact you've known since middle school science class. The closer two protons get to each other, the stronger this electrostatic repulsion becomes. It rises exponentially as distance decreases. For two protons to get close enough to fuse into a heavier nucleus, they need to overcome this Coulomb barrier, named after French physicist Charles-Augustin de Coulomb, who first described electrostatic forces mathematically. The Coulomb barrier is extraordinarily high. To overcome it classically, protons would need to have kinetic energies corresponding to temperatures of billions of degrees, not millions. At 15 million degrees, protons in the Sun's core move fast, certainly, with average speeds of about 600 kilometers per second. That's fast enough to circle the Earth's equator in about a minute. But it's nowhere near fast enough to overcome the electrostatic repulsion between protons through brute force alone. If you actually do the calculation using classical physics, plugging in the numbers for the temperature in the Sun's core, the electric charge of protons, and the distance they need to approach for fusion to occur, you find something deeply disturbing. The probability that two protons could get close enough to fuse is approximately 10 to the negative 290. That's a decimal point followed by 289 zeros and then a 1. To put this in perspective, there are only about 10 to the 80 atoms in the entire observable universe. The probability we're talking about is so fantastically small that it's essentially zero. It should never happen. Not once in the lifetime of the universe. Not once in a trillion lifetimes of the universe. And yet the Sun does shine. It's been shining steadily for about 4.5 billion years, fusing hydrogen into helium at a prodigious rate. Every single second, The Sun converts about 600 million tons of hydrogen into 596 million tons of helium. The missing 4 million tons of mass is converted directly into energy, according to Einstein's most famous equation, E equals mc squared. This energy streams out into space as light and heat, warming our planet, driving our weather systems, enabling photosynthesis, making life possible. Everything you see, touch, taste, and experience depends on the sun shining. You are here, conscious and wondering about quantum mechanics because the sun shines. So something is clearly, fundamentally, completely wrong with the classical calculation. The universe is telling us, through the simple fact that we exist, that classical physics cannot be the whole story. Enter quantum mechanics and the phenomenon of tunneling. Protons in the sun's core don't behave as classical particles with definite positions and trajectories. They behave as quantum waves, with their positions described by probability distributions. Even though protons don't have enough energy to classically overcome the Coulomb barrier, their quantum wave functions extend through the barrier. There's a probability, enhanced by quantum mechanics, that two protons will tunnel through their mutual repulsion and get close enough for the strong nuclear force to grab them and fuse them together. This probability is still extremely small for any given pair of protons. The average proton in the sun's core has to wait about 10 billion years before it successfully fuses with another proton. That's longer than the current age of the universe. But there are so many protons in the sun's core, an almost incomprehensibly large number, that these rare fusion events happen constantly, about 10 to 38 times per second in the sun as a whole. The sheer number of protons compensates for the incredibly low probability of any individual fusion event. Without quantum tunneling, the sun wouldn't shine. In fact, most stars wouldn't shine at all. Red dwarf stars, which are by far the most common type of star in the universe, have even lower core temperatures than the sun. According to classical physics, they absolutely shouldn't be able to sustain fusion. Yet they do, some of them burning steadily for trillions of years. Quantum mechanics makes the routine impossible. But quantum tunneling doesn't just power stars. It's also essential to technologies you use every day. The scanning tunneling microscope, invented in 1981, uses quantum tunneling of electrons to image individual atoms on surfaces. A sharp metal tip is brought incredibly close to a conducting surface, close enough that electrons can tunnel through the vacuum gap between them. By measuring the tunneling current and scanning the tip across the surface, scientists can map out the positions of individual atoms with extraordinary precision. This technology has been fundamental to the development of nanotechnology and modern electronics. Quantum tunneling also plays a crucial role in DNA mutations and chemical reactions in living cells. Enzymes, the molecular machines that facilitate chemical reactions in your body, often work by lowering energy barriers that reactants need to overcome. But even with the barrier lowered, quantum tunneling can allow reactions to proceed faster than classical physics would predict. Some scientists think that quantum tunneling might even play a role in the mutations that drive evolution, allowing protons to hop between DNA base pairs in ways that wouldn't be classically possible. The phenomenon is both utterly bizarre and absolutely essential. Particles genuinely don't have enough energy to be where they end up. They tunnel through barriers that should be impenetrable. They do the impossible billions of times per second throughout the universe. And without this quantum weirdness, you wouldn't be here to wonder about it. Now we're going to explore what might be the most mind-bending aspect of quantum mechanics. The phenomenon that made Albert Einstein so uncomfortable that he spent years trying to prove it couldn't be true. He failed. The phenomenon is real, and it suggests that the universe is far more interconnected, far more unified than anything our everyday experience prepares us for. It's called quantum entanglement, and Einstein dismissively referred to it as spooky action at a distance. Here's the basic idea. When two particles interact in certain ways, they can become entangled, linked together in a quantum state such that they're no longer independent objects. Even if you then separate these particles by vast distances, they remain mysteriously connected. Measure one particle, and you instantly affect the state of its entangled partner, regardless of how far away it is. This isn't just correlation in the normal sense. If I take two coins and put one in a box that goes to New York and another in a box that goes to Los Angeles, and you open the New York box and find heads, then you immediately know the Los Angeles box contains tails, assuming I set them up that way. But that's just because the coins had definite states all along. You just didn't know what they were until you looked. Quantum entanglement is fundamentally different. Before measurement, neither particle has a definite state. They exist in superposition, simultaneously in all possible states at once, but they're correlated superpositions. The particles share a single quantum state, even though they might be on opposite sides of the galaxy. When you measure one particle and it chooses a state, let's say spin up, the other particle instantly knows to be in the opposite state, spin down, maintaining their quantum correlation. Imagine two quantum coins that are entangled. While they're flying through the air, neither is definitively heads or tails. Each exists in a superposition of both possibilities simultaneously. But they're entangled, so their states are correlated. The moment one coin lands and chooses heads, the other instantly becomes tails, no matter how far away it is. Not because information traveled from one coin to the other, but because they share a single quantum state that extends across space. Einstein found this deeply, viscerally troubling. He believed, based on his theory of special relativity, that no information could travel faster than light. The speed of light was supposed to be the universe's absolute speed limit, an unbreakable cosmic law. And yet entanglement seemed to require some kind of instantaneous influence between distant objects, faster than light communication of some sort. It violated everything Einstein thought he understood about how the universe worked. In 1935, Einstein and his colleagues Boris Podolsky and Nathan Brosen wrote what's now called the EPR paper, named after their initials. They argued that quantum mechanics must be incomplete. There must be hidden variables, they said, secret properties that particles carry with them that predetermine their measurement results. These hidden variables would create the illusion of spooky action at a distance. The particles aren't really influencing each other instantaneously. They just both received instruction sets when they were created, and they're following those instructions locally. It was an elegant argument, and it seemed to restore sanity to physics. The universe could go back to being local, with influences traveling at or below the speed of light. Everything could be explained by properties of objects themselves, not by mysterious quantum connections. For nearly 3 decades, this debate remained purely philosophical. There seemed to be no way to experimentally test whether Einstein or the quantum mechanical view was correct. Then in 1964, Irish physicist John Stuart Bell changed everything. He derived a mathematical theorem, now called Bell's theorem, showing that if Einstein's hidden variables existed, and if they obeyed reasonable assumptions about locality, they would lead to measurable predictions that differ from quantum mechanics. The predictions could be expressed as inequalities, mathematical relationships between measurement results that hidden variable theories must satisfy but quantum mechanics violates. Experiments could finally decide between Einstein's view and quantum mechanics. The question could be answered empirically, and starting in the 1970s with groundbreaking experiments by John Clauser and later by Alain Aspect in France, experiments began testing Bell's inequalities. The results were unambiguous. Quantum mechanics was right. Einstein's hidden variables were wrong. The correlations between entangled particles violated Bell's inequalities exactly as quantum mechanics predicted. The spooky action at a distance was real. No local hidden variables could explain the results. The universe really is non-local at the quantum level. These experimental confirmations of quantum entanglement and violations of Bell's inequalities continued through the following decades, becoming increasingly sophisticated and closing various potential loopholes. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their pioneering experiments with entangled photons and tests of Bell's inequalities. The Nobel Committee recognized that these experiments had established entanglement as an indisputable feature of nature and opened up the field of quantum information science. But the experiments testing and confirming entanglement didn't stop there. They've only become more impressive, more ambitious, and more profound in their implications. In 2024, physicists achieved something remarkable at CERN, the European Organization for Nuclear Research in Switzerland, home to the Large Hadron Collider. They observed quantum entanglement between top quarks, the heaviest known fundamental particles, at collision energies of 13 tetraelectron volts. This is the highest energy scale at which entanglement has ever been observed, opening up entirely new ways to study quantum mechanics and potentially search for physics beyond the standard model of particle physics. What makes this particularly significant is that top quarks are exotic, massive particles that exist for only about 1/60th of a second before decaying into other particles. They're far removed from the light, easily manipulated photons typically used in entanglement experiments. Yet even these massive fleeting particles showed clear quantum entanglement, demonstrating that these quantum correlations persist even at the extreme energy scales and short time scales accessible only at the world's most powerful particle colliders. The quantum nature of reality extends all the way up to the highest energy processes we can currently probe. In late 2024 and early 2025, quantum entanglement experiments expanded into space. A tiny device called SEAQ, the Spacey Entanglement and Annealing Quantum Experiment, about the size of a shoebox, was installed on the outside of the International Space Station. It successfully created entangled photon pairs in space and measured them with extraordinary precision, achieving stronger violations of Bell's inequality than previous space-based experiments. This is a crucial step toward building a global quantum communication network that could enable completely secure transmission of information across continents and oceans. In 2025, the Jinan-1 microsatellite established a quantum connection between China and South Africa spanning nearly 13,000 kilometers, demonstrating that entanglement can be maintained across vast distances. Scientists are now working on ambitious plans for continent-scale networks of vacuum-sealed tubes that could transmit quantum information at rates exceeding 10 trillion qubits per second. We're moving from proving that entanglement exists to actually engineering it for practical purposes. But what does entanglement really mean for our understanding of reality? One interpretation is that space itself, the separation between objects, isn't as fundamental as it appears. If particles can maintain instant correlations across arbitrary distances, perhaps they were never truly separate to begin with. Maybe the universe is fundamentally non-local, with apparent separations being illusions created by our limited classical perspective. In this view, everything is connected to everything else at the deepest quantum level. The universe is a single, unified quantum system in which the boundaries between objects are more apparent than real. Some physicists even speculate that quantum entanglement might be the fundamental glue that holds space-time itself together. The geometry of the universe might emerge from patterns of quantum correlations between more fundamental degrees of freedom. Space and time wouldn't be the stage on which quantum mechanics plays out. Instead, they would be emergent properties of quantum entanglement itself, approximate descriptions that break down at the smallest scales. This leads to some fascinating possibilities. If particles that were once entangled remain connected regardless of distance, then every atom in your body, which was forged in the hearts of ancient stars and scattered across space by supernovae, might still maintain subtle quantum correlations with particles throughout the universe. You might be more cosmically connected than you ever imagined, not in some vague metaphysical sense, but through genuine quantum mechanical relationships that can be mathematically described and experimentally verified. Recent research has even revealed quantum entanglement operating in biological systems. When plants perform photosynthesis, converting sunlight into chemical energy, they use quantum entanglement between photons to enhance efficiency. Multiple pathways are explored simultaneously through quantum superposition, allowing energy to find the optimal route through the plant's molecular machinery. Every leaf is performing quantum computations more sophisticated than anything we've managed to build artificially. Some scientists speculate that quantum entanglement might play a role in bird navigation, allowing them to sense Earth's magnetic field through quantum effects in special proteins in their eyes. Others think entanglement might be important for enzyme function, and even for the unity of conscious experience, the way disparate sensations and thoughts combine into a single, coherent awareness. Your sense of being a unified self rather than a collection of separate mental processes might arise from quantum correlations between different regions of your brain. These ideas remain speculative and controversial, but they point to something profound. Quantum entanglement isn't just an abstract phenomenon studied in physics laboratories. It might be woven into the fabric of life itself, operating in your body right now, in ways we're only beginning to understand. The boundaries between quantum mechanics and biology, between physics and consciousness, might be far more blurred than we ever suspected. Let's now confront one of the most philosophically troubling aspects of quantum mechanics, the measurement problem. We've talked about how particles exist in superposition until they're observed or measured, at which point the superposition collapses and the particle suddenly has a definite state. But what exactly constitutes a measurement? What counts as observation? Does it require a conscious observer? Or is any interaction with the environment sufficient? And what happens to all those other possibilities that didn't occur? The famous Schrodinger's cat thought experiment illustrates the puzzle beautifully. Imagine a cat sealed in a box with a quantum particle that has a 50% chance of decaying within an hour. If the particle decays, it triggers a device that kills the cat. According to quantum mechanics, before you open the box, the particle exists in a superposition of decayed and not decayed states. But what about the cat? Is it also in a superposition of alive and dead states until you open the box and observe it? Most physicists today don't think consciousness is necessary for quantum measurement. The cat being a large, complex object constantly interacting with air molecules and electromagnetic radiation in its environment would cause the quantum superposition to collapse almost immediately through a process called decoherence. The quantum information that would maintain the superposition gets rapidly dispersed into the environment, becoming effectively impossible to recover. The quantum world transitions into the classical world of definite properties. Decoherence explains why we don't see quantum effects like superposition in our everyday lives. The larger and warmer an object is, the more it interacts with its environment, and the faster decoherence occurs. At room temperature in air, quantum superpositions of macroscopic objects collapse almost instantly. This is why quantum computers need to be cooled to temperatures approaching absolute zero and isolated from vibrations and electromagnetic noise. Any interaction with the environment can destroy the delicate quantum states they rely on. But decoherence doesn't fully solve the measurement problem. The mathematics of quantum mechanics suggest that all possible outcomes of a measurement continue to exist in some sense, even after decoherence. The wave function doesn't truly collapse. It just appears to collapse from the perspective of any particular observer who becomes entangled with one branch of the wave function. This leads to the many worlds interpretation, one of the most radical ideas in all of physics. According to this interpretation, every time a quantum measurement occurs, the universe splits into multiple branches, one for each possible outcome. In one branch, Schrödinger's cat lives. In another, it dies. In one branch, the particle decayed. In another, it didn't. All outcomes are equally real. They all happen. We just only experience one branch. If many worlds is correct, then every quantum interaction creates new branches in the universal wave function. Every time an electron in your brain takes one path rather than another through a quantum superposition, the universe splits. There are countless versions of you reading this sentence, each in a slightly different universe where quantum events played out differently. Every quantum event that could have multiple outcomes does have multiple outcomes, just in different branches of reality that can't communicate with each other. This interpretation sounds like science fiction, but it's taken seriously by many physicists because it's the most straightforward reading of the mathematical formalism of quantum mechanics. You take the equations at face value without adding anything extra like wave function collapse. The price you pay is accepting an infinity of parallel universes, an ever-branching tree of realities encompassing all possibilities. Most physicists find this price too high to pay, but the interpretation remains on the table. Other interpretations exist. The Copenhagen interpretation says we shouldn't worry too much about what's happening when we're not measuring. Quantum mechanics tells us how to calculate the probabilities of measurement outcomes, and that's enough. Don't ask what the particle is really doing between measurements. The pilot wave interpretation says particles do have definite positions, but they're guided by a mysterious wave that fills all of space and instantaneously responds to configurations throughout the universe. The relational interpretation says quantum states only have meaning relative to particular observers, not in any absolute sense. A century after its founding, quantum mechanics remains an extraordinarily successful theory empirically, yet profoundly mysterious conceptually. We can calculate anything we want to extraordinary precision, but we still argue about what it all means. In 2025, At a conference celebrating the 100th anniversary of quantum mechanics, physicists engaged in heated debates that would have been familiar to the founders of the theory. The mystery, it seems, is built into the heart of reality itself. Now let's dive even deeper, beyond particles, and into the quantum field theory that modern physics uses to describe reality at its most fundamental level. What we call particles might not be fundamental at all. They might be temporary disturbances in underlying fields that permeate every inch of space. Imagine the surface of a perfectly still pond. Now drop a stone into the water. Ripples spread outward, waves carrying energy and information across the liquid surface. In quantum field theory, particles are like those ripples. Except, instead of water, they're disturbances in invisible fields that fill all of space and time. There's an electron field permeating every point in the universe. When this field gets excited in just the right way, we observe what we call an electron. But the electron isn't really a tiny ball of matter zipping around. It's more like a persistent wave pattern in an underlying medium we can never directly perceive. The photons carrying light to your eyes right now are ripples in the electromagnetic field. The quarks that make up the protons and neutrons in your body are excitations in quark fields. This means empty space isn't empty at all. It's filled with an infinite number of quantum fields, each capable of producing particles when excited with sufficient energy. The vacuum of space is like an ocean that appears calm on the surface but teems with potential wave patterns waiting to emerge. And these fields aren't just sitting there passively. They're fluctuating, seething with quantum activity even in what we call empty space. These quantum vacuum fluctuations aren't just mathematical abstractions. They have real, measurable effects. There's a phenomenon called the Casimir effect that beautifully demonstrates this. Take two uncharged metal plates and place them very close together in a vacuum. The quantum fluctuations of electromagnetic fields between the plates become restricted compared to the fluctuations outside. This creates a measurable force pushing the plates together, as if the vacuum itself has structure and pressure. Empty space, it turns out, is full of invisible quantum activity. These vacuum fluctuations involve virtual particles, fleeting quantum entities that pop into existence for incredibly brief moments before disappearing. They borrow energy from the future, exist for a time so short that the universe's uncertainty doesn't notice, then pay the energy back before anyone can catch them, violating energy conservation. It sounds absurd, but virtual particles are real in the sense that they produce measurable effects. They cause slight shifts in atomic energy levels that have been measured with extraordinary precision. They mediate forces between particles. The entire framework of modern particle physics relies on virtual particles and quantum fields. This quantum vacuum is thought to be related to dark energy, the mysterious force that's causing the expansion of the universe to accelerate. Some physicists think the energy density of the quantum vacuum might be driving cosmic expansion, though the calculations are notoriously difficult and the theoretical predictions don't match observations. Nevertheless, it's possible that quantum processes on the tiniest scales influence the fate of the entire universe, demonstrating a profound interconnectedness between the quantum and cosmic realms. But quantum field theory reveals something even stranger about the nature of time itself. In the mathematics of quantum field theory, particles can travel backward in time. An electron moving backward through time is mathematically identical to a positron, an antiparticle, moving forward through time. This led physicist John Wheeler to propose a wild idea. Maybe there's only one electron in the entire universe, zigzagging back and forth through time, appearing as countless particles and antiparticles from our forward time perspective. While Wheeler's one-electron universe remains speculative, the underlying principle reveals something profound. The distinction between past and future, between particle and antiparticle, becomes fluid at the quantum level. Time isn't the simple one-way flow we experience in daily life. It's something stranger, more flexible, woven into the quantum structure of reality in ways that defy our intuitions. This temporal flexibility shows up in various quantum phenomena. Quantum tunneling, as we discussed, allows particles to borrow energy from the future. The Hawking radiation that causes black holes to slowly evaporate involves particle pairs where one partner falls into the black hole while the other escapes. But the mathematics requires treating the infalling particle as if it's traveling backward in time. Delayed Coyce experiments suggest that future measurements can influence past events. All of this forces us to reconsider the most basic questions about existence. What does it mean to be real in a universe where particles exist in multiple states simultaneously, where empty space teems with virtual activity? Where can the future influence the past? How do we understand identity and persistence when the fundamental constituents of matter are temporary excitations in underlying fields? Perhaps reality isn't made of things at all, but of relationships, patterns of quantum correlations that we interpret as objects. Now let's turn to one of the most exciting frontiers in quantum physics, the quantum computing revolution that's currently unfolding. For decades, quantum computing existed primarily as a theoretical possibility. A fascinating idea that might work someday if we could overcome enormous technical challenges. But in the past few years, and especially in 2024 and 2025, quantum computing has transformed from a distant dream into an emerging reality. Here's the basic idea of how quantum computers work. Classical computers use bits that can be either 0 or 1, off or on. They process information by manipulating these bits according to logical rules. Quantum computers use qubits, quantum bits that can be in a superposition of 0 and 1 simultaneously. A qubit can be both 0 and 1 at the same time until you measure it, at which point it collapses to one state or the other. This might not sound like much, but it leads to exponential increases in computational power. Two classical bits can be in one of four states at any moment: 0, 0, 0, 1, 10, or 11. But two qubits can be in a superposition of all four states simultaneously. 3 qubits can represent 8 states at once. The number of states grows exponentially with the number of qubits. With just 300 qubits in perfect superposition, you could represent more states simultaneously than there are particles in the observable universe. This allows quantum computers to solve certain problems dramatically faster than classical computers ever could. Tasks like factoring large numbers, searching databases, simulating quantum systems, and optimizing complex networks that would take classical computers thousands or millions of years could potentially be done in hours or minutes. The implications for cryptography, drug discovery, material science, artificial intelligence, and fundamental physics research are profound. But building a practical quantum computer is extraordinarily, almost impossibly difficult. The quantum superpositions that qubits rely on are incredibly fragile, more delicate than anything else in nature. Any interaction with the environment, any vibration, no matter how slight, any temperature fluctuation, no matter how small, Any electromagnetic noise from nearby electronics, even a single stray photon from the environment, can cause decoherence. And decoherence destroys the quantum states that make quantum computing possible. The qubits collapse from useful superpositions into definite classical states before the computation finishes. It's like trying to build the most intricate house of cards imaginable during an earthquake, while someone nearby operates a leaf blower. The more qubits you have, and the longer your computation runs, the more opportunities there are for errors to accumulate. And quantum errors are particularly insidious because you can't simply copy quantum information to back it up. There's a fundamental theorem in quantum mechanics called the no-cloning theorem that says you can't make perfect copies of unknown quantum states. You can't just save your work and reload if something goes wrong. For decades, this seemed like an insurmountable barrier. Quantum computers could work in principle, but actually building ones that could outperform classical computers on useful problems seemed perpetually just out of reach. Year after year, researchers would demonstrate small quantum systems with a handful of qubits, but they couldn't scale up. Every time you added more qubits, the error rates got worse, not better. It was like trying to climb a mountain that gets steeper the higher you go. The key breakthrough needed to make quantum computers practical is something called quantum error correction. This is the ability to detect and fix errors that occur during computation without destroying the quantum information you're trying to preserve. It sounds impossible. How can you measure whether an error occurred without measuring the quantum state and thereby destroying the superposition? The answer is ingenious and relies on encoding quantum information redundantly across multiple physical qubits. Here's the basic idea. Instead of storing one bit of quantum information in one physical qubit, you encode it across many physical qubits in a clever way. These physical qubits become correlated through entanglement such that you can measure certain properties of the group without learning anything about the encoded quantum information. If an error occurs in one of the physical qubits, you can detect it by checking these correlations and correct it before it propagates and ruins the entire computation. It's like storing your data across multiple hard drives with sophisticated error-checking algorithms. Except it's vastly more subtle because you're dealing with quantum superpositions. The challenge is that quantum error correction requires significant overhead. You need many physical qubits to encode each logical qubit, the useful unit of quantum information that actually performs your computation. Early estimates suggested you might need thousands or even millions of physical qubits to encode a single error-corrected logical qubit. This seemed prohibitively expensive, putting useful quantum computers decades or centuries away. But in 2024, two research teams made groundbreaking advances that transformed the field overnight. A team at Harvard University and MIT, working with the quantum computing startup Q-ray Computing, demonstrated a quantum processor containing 48 logical qubits. To put this in perspective, previous experiments had achieved only a handful of logical qubits at most. Going from 5 or 10 to 48 represents an exponential leap in capability. And crucially, they showed that these logical qubits could perform operations, the basic building blocks of computation, while maintaining their quantum coherence. The system actually worked as a quantum computer, not just as a physics experiment. Simultaneously and independently, Google announced their Willow quantum processor in late 2024, demonstrating something even more fundamental. They achieved exponential error suppression, showing that as you increase the number of physical qubits used to encode each logical qubit, the error rate decreases exponentially rather than staying constant or increasing. This is the holy grail of quantum computing, the break-even point that proves the technology can scale. It means that in principle, you can build arbitrarily large, arbitrarily accurate quantum computers simply by adding more physical qubits. The errors don't overwhelm you as you scale up. The technology has crossed a threshold. These breakthroughs were so significant that Physics World magazine named them joint winners of the 2024 Breakthrough of the Year, calling them the defining challenge for quantum computing. And they came to fruition in time for the International Year of Quantum Science and Technology in 2025, which marks the centennial of quantum mechanics. To top it off, the 2025 Nobel Prize in Physics was awarded to John Clark, Michel Deverett, and John Martinez for their foundational work in the 1980s on superconducting quantum circuits, the technology that underlies quantum computers from Google, IBM, and many other companies. Their discovery that quantum effects can show up even in large-scale superconducting circuits was essential for making quantum computing possible. The fact that they received the prize in 2025 demonstrates how this work has transformed from fundamental physics into world-changing technology. The quantum computing industry is now attracting massive investment. Quantum computing startups raised nearly $4 billion in equity funding in the first 9 months of 2025 alone, almost triple the amount raised in all of 2024. National governments invested $10 billion by April 2025. Stock prices of publicly traded quantum computing companies increased by over 3,000% in a single year. This isn't hype. It's a genuine revolution in computing power based on fundamental quantum mechanical principles. Within the next decade, quantum computers are expected to tackle problems completely out of reach of classical machines. They'll design new drugs by simulating molecular interactions with perfect accuracy. They'll discover new materials with properties we've never seen before. They'll optimize logistics networks, financial systems, and energy grids. They'll advance artificial intelligence in ways we can't yet predict. And they'll help us understand the quantum nature of reality itself by simulating quantum systems that are too complex to analyze mathematically. We're witnessing the transition of quantum mechanics from a century-old theory to the foundation of 21st century technology. The impossible is becoming routine. The theoretical is becoming practical, and the quantum world is becoming increasingly accessible to human engineering and control. Now let's explore one of the most tantalizing frontiers in quantum research, the possibility that life itself operates using quantum mechanical principles. For decades, scientists assumed that the warm, wet, noisy environment inside living organisms would immediately destroy any quantum effects. Cells are far too hot and complex for quantum coherence to survive. Or so the conventional wisdom went. Life operated purely according to classical physics. But recent discoveries have shattered this assumption, revealing that nature has been exploiting quantum mechanics for billions of years in ways that are only now coming to light. And the implications are profound. If life uses quantum mechanics, then you are quite literally a quantum organism. And every thought in your mind might emerge from quantum processes. Consider photosynthesis, the process by which plants, algae, and some bacteria convert sunlight into chemical energy. Classical physics suggested that energy from absorbed photons should randomly bounce around inside the plant's molecular machinery, losing much of its potency before reaching the reaction center where it's converted to chemical form. The efficiency should be fairly low, maybe 20 or 30% at best. But experiments reveal something astonishing. Photosynthesis achieves near-perfect energy transfer, approaching 95 to 99% efficiency. How? Through quantum coherence. When a photon is absorbed by a pigment molecule in the plant, it creates a quantum excitation, an exciton, that exists in a superposition of multiple pathways simultaneously. The exciton explores all possible routes through the molecular maze at once, existing in a superposition state where it's simultaneously traveling down every path. Through quantum interference, the paths that lead nowhere cancel out, while the optimal path is enhanced. The exciton finds the reaction center with extraordinary efficiency by quantum mechanical trial and error. This isn't just clever design. It's quantum computing performed by molecules. Every leaf on every tree is performing quantum computations more sophisticated than anything we've built in our laboratories. Plants have been quantum computers for billions of years, harnessing superposition and quantum coherence to optimize energy transfer in ways that classical processes could never achieve. But photosynthesis isn't the only place where life exploits quantum mechanics in sophisticated ways. There's growing, increasingly compelling evidence that bird navigation relies fundamentally on quantum effects, specifically on quantum entanglement occurring in molecules in their eyes. Many species of birds can detect Earth's magnetic field with extraordinary sensitivity that seems impossible to explain through classical physics alone. They use this magnetic sense to navigate across thousands of miles during migration, finding their way between specific locations with remarkable precision year after year. The leading scientific theory for how birds accomplish this remarkable feat involves special proteins called cryptochromes found in their retinas. When blue light strikes these proteins, it creates pairs of electrons that become quantum entangled through a chemical reaction. These entangled electron pairs are exquisitely sensitive to magnetic fields through a process called the radical pair mechanism, a quantum mechanical effect with no classical analog. Here's how it works in more detail. The light-activated cryptochrome protein contains molecules that, when struck by a photon, transfer an electron from one molecule to another. This creates two molecules, each with an unpaired electron, a configuration called a radical pair. These two unpaired electrons are quantum mechanically entangled. Their quantum spins are correlated in ways that depend on the strength and direction of any external magnetic field they're immersed in, including Earth's weak magnetic field. The quantum states of these entangled electrons evolve differently depending on the magnetic field's orientation. Some spin configurations lead to chemical reactions that regenerate the original molecules. Other configurations lead to different reaction products. The ratio of these two outcomes depends on the magnetic field direction. Crucially, the quantum coherence between the entangled electrons must be maintained for at least microseconds, possibly milliseconds, for the effect to work. During this time, the entanglement has to survive in the warm, noisy, wet environment of a living cell inside a bird's eye. Until recently, this seemed implausible. Quantum coherence times in biological systems were thought to be far too short for this mechanism to work. But experiments conducted in 2024 demonstrated quantum coherence in cryptochrome proteins persisting for times long enough to be biologically relevant. The birds literally see the magnetic field as a pattern of light and dark superimposed on their visual perception. A quantum compass built directly into their visual system. They're using quantum entanglement to navigate, exploiting one of the strangest features of quantum mechanics for a practical biological purpose. Quantum effects also appear crucial for enzyme function throughout biology, including in your body right now. Enzymes are biological catalysts, proteins that speed up chemical reactions by enormous factors, sometimes by millions or billions of times. They're essential for life. Nearly every chemical reaction in your body, from digesting food to synthesizing DNA to producing energy in your cells, is catalyzed by enzymes. Without enzymes, these reactions would occur so slowly that life would be impossible. Enzymes work partly by providing a structure that brings reacting molecules into the right orientation, and partly by lowering the energy barriers that reactants need to overcome. But even with these classical effects, many enzyme-catalyzed reactions are faster than classical chemistry predicts. The missing ingredient appears to be quantum tunneling. Hydrogen atoms and protons, being the lightest atomic particles, have significant quantum mechanical wave properties. They can tunnel through energy barriers rather than going over them. Some enzymes appear to have evolved specifically to exploit quantum tunneling. They position atoms at precisely the right distances to maximize tunneling probability. The protein structure creates a geometric arrangement where quantum mechanical wave functions of reactants extend through barriers to reach product states with unusually high probability. Recent studies have found evidence for quantum tunneling in numerous enzymes, from those involved in alcohol metabolism to those that maintain DNA integrity. Your cells are performing quantum computations billions of times per second to keep you alive. This quantum nature of enzyme function has profound implications for evolutionary biology. If quantum tunneling affects reaction rates and chemical pathways in cells, it could influence mutation rates in DNA. Protons can tunnel between DNA base pairs during replication, potentially causing mutations that wouldn't occur through classical means alone. Some researchers speculate that quantum mechanics might influence not just the rate of evolution, but possibly even its direction, affecting which mutations are more likely to occur. Life might be shaped by quantum mechanics at its most fundamental level, but the most speculative, controversial, and potentially profound idea is that consciousness itself might fundamentally involve quantum mechanical processes. This hypothesis, most famously proposed by mathematical physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff, suggests that quantum effects in the brain's microtubules might be essential for conscious experience. Microtubules are tiny protein structures, hollow tubes about 25 nanometers in diameter, that form the structural skeleton inside neurons and other cells. Penrose and Hameroff's theory, called orchestrated objective reduction, or ORC, proposes that microtubules can maintain quantum coherence, existing in superpositions of different structural configurations. These quantum superpositions could allow microtubules to act as quantum computers, processing information in ways that classical neural networks alone could not achieve. When the superposition reaches a critical threshold related to the difference in space-time curvature between the superposed states, it undergoes objective reduction, collapsing into a definite state. This collapse, according to the theory, corresponds to a moment of conscious awareness, a quantum event that underlies subjective experience. The theory remains highly controversial and is viewed with skepticism by many neuroscientists. The main objection has always been that the brain is far too warm, wet, and noisy for quantum coherence to survive long enough to matter for neural processing. Decoherence times in such an environment were thought to be far too short, measured in femtoseconds or picoseconds, much too brief to influence brain function meaningfully. However, Recent research is challenging these assumptions. In 2024, scientists discovered quantum effects operating at room temperature in certain biological molecules, persisting much longer than previously thought possible. While this doesn't prove the urge or theory correct, it does show that biology can maintain quantum coherence in ways we didn't think possible. The question has shifted from whether quantum effects can exist in biological systems to how widespread and important they actually are. If consciousness does involve quantum processes, even if not in the specific way Penrose and Hameroff propose, this would have revolutionary implications. Consciousness wouldn't be merely an emergent property of classical computation in neural networks. It would be fundamentally woven into the quantum structure of reality, potentially as basic as space, time, and energy. The hard problem of consciousness, the question of how subjective experience arises from objective physical processes, might be intimately connected to the measurement problem in quantum mechanics. The question of how quantum superpositions collapse into definite states. Mind and matter might be different aspects of quantum reality rather than separate substances. The observer effect in quantum mechanics, the way measurement affects quantum systems, might be fundamentally related to consciousness. Some interpretations of quantum mechanics suggest that consciousness plays a special role in collapsing wave functions, transforming quantum possibilities into classical actualities. If true, conscious beings wouldn't be passive observers of a predetermined reality. They would be active participants in its ongoing creation, quantum artists painting existence through the brushstrokes of awareness. These ideas remain on the frontier of science, not yet fully established, but no longer easily dismissed. What's clear is that quantum mechanics operates throughout the living world in ways we never suspected. You are not just a classical machine that happens to be made of quantum particles. You might be a fundamentally quantum organism, using superposition, tunneling, and entanglement to function in ways that classical physics alone could never achieve. The boundary between quantum and classical, between physics and biology, between matter and mind, is far more blurred than anyone imagined even a decade ago. Let's now confront some of the deepest implications of quantum mechanics for our understanding of reality, time, and causality. We've talked about various weird quantum phenomena, but now we need to grapple with what they actually mean for the nature of existence itself. One of the most philosophically troubling aspects of quantum mechanics is the delayed choice experiment, which suggests that the future can influence the past. Let me describe a specific version of this experiment that pushes our intuitions to the breaking point. In a standard double-slit experiment, a photon travels through both slits simultaneously as a wave, creating an interference pattern. If you place detectors at the slits to see which one the photon goes through, the interference pattern disappears and the photon behaves like a particle. So far, so weird, but at least the measurement happens before the photon reaches the final detection screen. But what if you wait until after the photon has passed through the slits to decide whether to measure which path it took? This can be done using special optical devices that can be rapidly switched on or off. Here's what happens. You send a photon toward the double slits. It passes through, existing in a superposition of going through both slits. It's heading toward the detection screen. At this point, it's already committed to being a wave, right? The interference pattern should appear. But now, in the incredibly brief time between when the photon passed through the slits and when it reaches the detection screen, you make a decision. You either measure which path it took or you don't. Remarkably, this future choice, made after the photon has already passed through the slits, determines whether the interference pattern appears. If you measure the path, even retroactively, the photon behaves as if it went through only one slit all along. If you don't measure the path, it behaves as if it went through both slits simultaneously. The choice made in the future influences the photon's behavior in the past. This has been demonstrated experimentally many times. In 2007, a team in France performed a version using single photons and beam splitters, confirming the predictions of quantum mechanics. Time, it seems, isn't the rigid one-way flow we experience in daily life. At the quantum level, causality becomes more flexible, more mysterious. This temporal strangeness connects to another profound aspect of quantum mechanics, the relationship between possibility and actuality. In our everyday experience, we think of possibilities as mere abstractions, mental concepts we use to describe our ignorance about what's actually real. The ball is in this box or that box. We don't know which until we look, but it was always in one box or the other. Possibilities aren't real. Only actualities are real. Quantum mechanics suggests otherwise. The mathematics of quantum theory treats superposition states as ontologically real, not just expressions of ignorance. Before measurement, the particle isn't in some definite state that we just don't know. It genuinely exists in all possible states simultaneously. Possibilities are real. The wave function encodes real possibilities that exist in the physical world, not just in our minds. When a measurement occurs, one possibility becomes actual while the others somehow cease to exist. Or, if you believe in many worlds, all possibilities remain actual in different branches of reality. Either way, quantum mechanics suggests that possibility and actuality are both fundamental features of reality, not that actuality alone is real and possibility is just our ignorance. This has profound implications for how we understand the universe's history. The past isn't a fixed record of what happened. It's more like a probability distribution over possible histories, and which history becomes actual depends on what measurements are made in the present. The delayed choice experiments demonstrate this explicitly. Your present observations help determine what happened in the past, not just what you know about the past. Some interpretations of quantum mechanics take this even further. In the participatory universe hypothesis proposed by physicist John Wheeler, conscious observers play a fundamental role in bringing reality into existence. The universe exists in a vast superposition of all possible states until conscious observation collapses it into specific realities. In this view, consciousness isn't merely an emergent property that arose late in cosmic evolution. It's a fundamental feature that participates in creating the very history of the universe. This might sound like solipsism or mysticism, but it's grounded in the mathematics and experimental results of quantum mechanics. The role of observation in determining reality is not optional. It's built into the theory. What remains controversial is whether conscious observation is special, or whether any physical interaction suffices. But either way, observation plays a fundamental role that has no parallel in classical physics. This brings us to the relationship between quantum mechanics and information theory. In recent decades, physicists have increasingly come to view information as more fundamental than matter or energy. In this view, the universe is essentially an information processing system. Particles and forces are manifestations of underlying informational structures. Every particle interaction is a computational step. Every quantum measurement is an information transaction. The entire cosmos is engaged in an incomprehensibly complex calculation. If information is fundamental, this resolves some puzzles about quantum mechanics. The reason particles exist in superposition until measured might be that information about their state hasn't been created yet. Measurement creates information, and with it, definite reality. The reason entanglement connects distant particles might be that they share quantum information that isn't localized in space. The particles aren't separate information systems. They're aspects of a single, non-local information structure. This informational view of reality connects to the holographic principle, one of the most radical ideas in theoretical physics. The holographic principle suggests that all the information contained in any region of space is encoded on its boundary. The three-dimensional volume is, in a sense, a projection of information stored on a two-dimensional surface, like a hologram. This idea arose from studying black holes. Stephen Hawking showed that black holes have entropy, a measure of information proportional to their surface area, not their volume. This suggests that the information content of a region of space is determined by the area of its boundary, not the volume it encloses. Some physicists think this applies to the entire universe. All the information about our three-dimensional reality might be encoded on a distant two-dimensional surface. If the holographic principle is correct, then our experience of living in three spatial dimensions might be an illusion. We might be more like characters in a cosmic hologram. Projections of information encoded in ways that transcend ordinary spatial relationships. Space itself might be an emergent property of more fundamental quantum information structures. These ideas remain speculative and controversial, but they're taken seriously by leading physicists precisely because quantum mechanics has already shown us that reality is far stranger than common sense suggests. Once you accept that particles can tunnel through barriers, exist in superposition, and remain entangled across cosmic distances, the idea that space might be holographic seems almost reasonable by comparison. All of this points toward a view of reality that's radically different from our everyday experience. The universe isn't made of solid objects moving through empty space according to deterministic laws. It's more like a vast quantum computer processing cosmic algorithms, exploring the space of possible realities through quantum superposition and interference. Matter is crystallized possibility. Space is a network of quantum correlations. Time is the flow of information processing, and consciousness might be the universe's way of experiencing these quantum computations from the inside. Now, as we bring this exploration toward its conclusion, let's reflect on what quantum mechanics means for you personally, for your existence, your consciousness, your place in the cosmos. Every breath you take right now involves quantum processes in your cells. Oxygen molecules binding to hemoglobin in your blood work through quantum chemistry. The electrons in the oxygen atoms exist in probability clouds, not at definite positions. They tunnel through energy barriers to form bonds. The very process keeping you alive is quantum mechanical. Every heartbeat depends on quantum tunneling in your nervous system. The electrical impulses that make your heart contract are mediated by ions passing through protein channels in cell membranes. These channels open and close through processes that involve quantum effects. Your heart knows how to beat because of quantum mechanics. Every thought in your mind, every moment of awareness, emerges from quantum processes in your brain. Action potentials propagating along neurons involve quantum tunneling of ions. The proteins that form synaptic connections fold into their functional shapes through quantum chemistry. The very substrate of consciousness, whatever consciousness ultimately is, operates according to quantum mechanical laws. You are quantum mechanics made conscious, a walking, thinking manifestation of the universe's most profound mysteries. The atoms that make up your body were forged in the hearts of dying stars billions of years ago through quantum nuclear fusion. Those atoms were scattered across space by supernova explosions and eventually gathered together by gravity to form the planet on which you evolved. But quantum mechanics suggests they might still maintain subtle entanglements with particles throughout the cosmos. You're not separate from the universe. You're a temporary pattern in the cosmic quantum field, intimately connected to everything that exists. The photons reaching your eyes right now have traveled through space, maintaining their quantum coherence across vast distances. They carry information about quantum processes occurring in distant stars, in the cosmic microwave background radiation left over from the Big Bang, in the quantum vacuum itself. Every moment of perception connects you directly to quantum processes throughout the universe. And if consciousness does play a role in quantum measurement, as some interpretations suggest, then every observation you make participates in creating reality. Every decision you choose helps determine which branch of the quantum wave function becomes actual. You're not a passive observer in a predetermined universe. You're an active participant in the ongoing creation of existence itself, collapsing quantum possibilities into definite realities through the very act of being conscious. This isn't mysticism, it's physics. It's the straightforward implication of taking quantum mechanics seriously and asking what it means for conscious beings like yourself. The universe revealed by quantum mechanics is one in which mind and matter, consciousness and cosmos, are profoundly interconnected. The boundaries between self and universe, between observer and observed, dissolve when you look closely enough at the quantum foundations of reality. As we move forward into the future of quantum science, the pace of discovery is accelerating. The year 2025 has been designated by the United Nations as the International Year of Quantum Science and Technology, marking a century since Werner Heisenberg first formulated quantum mechanics on the German island of Helgoland in 1925. In that 100 years, quantum mechanics has transformed from a strange, counterintuitive theory into the foundation of modern technology and our understanding of reality. The next 100 years promise to be even more revolutionary. Quantum computers will tackle problems completely beyond classical computation, potentially revealing entirely new physics. Quantum communication networks will enable perfectly secure information transmission across global distances. Quantum sensors will detect gravitational waves, dark matter, and other subtle phenomena with unprecedented sensitivity. Quantum biology will reveal how life harnesses quantum mechanics at the cellular and molecular level. And perhaps most profoundly, continued research into the foundations of quantum mechanics might finally resolve the century-old debates about what it all means. We might discover that consciousness is indeed a quantum phenomenon, that the many worlds interpretation is correct and parallel realities exist, or that space and time emerge from quantum information in ways we haven't yet imagined. Or we might find something even stranger, something that makes current quantum mechanics look as simple and incomplete as classical physics looked a century ago. What's certain is that the quantum world isn't finished surprising us. Every new generation of experiments reveals phenomena that challenge our understanding. In 2024 and 2025 alone, we've seen quantum entanglement verified at the highest energies ever tested. quantum coherence maintained in space, quantum error correction finally crossing the threshold for practical quantum computing, and Nobel Prizes awarded for work that's transforming quantum mechanics from theory to technology. The impossible has become routine, and the routine continues to astound us. As you go about your day after watching this, I want you to remember something profound about the nature of your existence. The world you see around you, solid and stable and comfortingly predictable, is an illusion created by your senses averaging over quantum fluctuations occurring too fast and too small for you to perceive directly. Every object you touch is mostly empty space, held together by quantum forces operating through virtual particle exchanges. Every color you see exists because electrons jump between quantized energy levels in atoms, emitting or absorbing photons with specific frequencies. Every breath you take, every thought you think, every moment of your existence emerges from quantum processes that defy classical logic and human intuition. But here's what I find most remarkable. Despite the strangeness, despite the counterintuitive weirdness, despite the fact that quantum mechanics violates everything our evolutionary experience prepared us for, it works. It works with extraordinary precision. It's been tested in countless experiments over 100 years, and it's never failed. Not once. Every prediction has been confirmed. Every application has succeeded. The computer or phone you used to watch this video operates because engineers successfully harnessed quantum effects in semiconductors. The GPS guiding you home works because it accounts for quantum mechanical effects on time itself. The medical imaging technologies that diagnose diseases rely on quantum principles. The lasers enabling fiber optic communication use quantum mechanics. We've learned not just to observe quantum mechanics, but to engineer it, to harness it, to make it work for us in practical technologies that transform human civilization. And we're just getting started. The quantum computers being developed now will tackle problems that classical computers could never solve, not in a billion years of calculation. Quantum communication networks will enable perfectly secure information transmission. Quantum sensors will detect gravitational waves from colliding black holes, subtle shifts in Earth's magnetic field, and perhaps even dark matter particles passing through the planet. Think about what humanity has accomplished in the century since quantum mechanics was discovered. We've gone from not understanding why heated objects glow, to building quantum computers that exist in superpositions of computational states. We've gone from puzzling over the photoelectric effect to creating quantum communication satellites that maintain entanglement across thousands of kilometers. We've gone from wondering why atoms don't collapse to engineering quantum sensors that can detect individual atoms. And we're accelerating. The pace of quantum technology development is increasing exponentially. The year 2025, as we record this video, marks the International Year of Quantum Science and Technology, celebrating the centennial of quantum mechanics. It's been exactly 100 years since Werner Heisenberg sat on the rocky island of Helgoland in the North Sea, suffering from hay fever, and formulated the first consistent version of quantum theory. In that century, quantum mechanics has transformed from a strange, controversial theory that even its founders didn't fully understand, into the bedrock foundation of modern physics and technology. But despite this success, despite the extraordinary precision of its predictions and the revolutionary technologies it's enabled, quantum mechanics remains deeply mysterious at a conceptual level. We still argue about what it means. Physicists still gather at conferences and debate, sometimes heatedly, what quantum mechanics actually tells us about the nature of reality. Is the wave function real, or just a calculational tool? Does observation create reality or just reveal it? Do parallel universes exist? Is consciousness special? These questions remain open, controversial, unresolved. You are not separate from the quantum mysteries we've explored tonight. You are these mysteries made conscious. You are quantum mechanics contemplating itself, asking questions about its own nature. The universe has spent nearly 14 billion years evolving the complexity necessary to support your particular pattern of awareness, arranging matter and energy in precisely the configuration needed for you to exist and wonder about existence. That's the ultimate quantum mystery. Not just that particles exist in superposition or that entanglement connects distant systems, but that the universe has organized itself into structures capable of asking why. Your consciousness is the universe experiencing itself, and quantum mechanics is the language it uses to do so. If you found this exploration into the quantum foundations of reality fascinating, I'd be incredibly grateful if you'd hit that like button and subscribe to the channel. This kind of deep dive into the nature of existence takes a lot of research and effort to put together. And your support makes it possible to continue exploring these mind-bending topics. Share this video with anyone you think would appreciate having their reality fundamentally questioned. Drop a comment below about which aspect of quantum mechanics you find most puzzling or exciting. Let's keep this conversation going. The quantum world is vast, strange, and endlessly fascinating. We've only scratched the surface tonight, but I hope you're leaving with a sense of wonder about the true nature of the reality you inhabit. You're living in a quantum universe made of quantum particles, governed by quantum laws, and possibly participating in quantum processes every moment of your conscious existence. That's not just physics. That's poetry. That's the deepest mystery available to human contemplation. Thank you for joining me on this journey into the heart of quantum mechanics. Until next time, keep looking deeper. Keep questioning what seems obvious, and never stop marveling at the beautiful, impossible, quantum universe we call home.